Imagine this: a lump of heavily corroded bronze and wood pulled from the deep, dark waters off a remote Greek island. For decades, it sat, a seemingly insignificant relic in a museum storage room, its secrets locked away beneath layers of crust and time. But when those secrets finally began to reveal themselves, they didn't just add a new chapter to history, they utterly rewrote it.
Completely. Changed everything we thought we knew.
Okay, let's unpack this. Today, we're embarking on a deep dive into one of the most astonishing archaeological discoveries of all time, the Antikythera mechanism. We're going to explore its mind-bending complexity, its truly surprising purpose, and why this single ancient device forces us to fundamentally rethink the entire timeline of human technological advancement.
What's truly fascinating here, I think, is that this was far from a simple tool or just, a decorative artifact. This was an ancient Greek hand-powered orrery, essentially. A sophisticated mechanical model of the cosmos.
An orrery, like a clockwork solar system.
Exactly. And, most crucially, it's widely recognized as the oldest known example of an analog computer.
An analog computer from ancient Greece.
That's right. Our mission today is to truly understand how such an extraordinarily advanced device could have possibly existed 2 millennia ago, and what profound insights it offers us about the capabilities and genius of ancient Greek scientists and engineers.
You've given us a stack of sources, groundbreaking articles, meticulous research papers, and your own comprehensive notes, and we're going to extract the most important nuggets of knowledge and insight from all of them.
Yeah, synthesize it all.
Consider this your shortcut to being truly well-informed about this ancient marvel without having to dig through 2 decades of academic papers yourself. Get ready for an incredible journey back in time. 1. The astonishing discovery. From shipwreck to Prochronistic puzzle. Our story, like many of the greatest archaeological tales, begins not with an intentional search, but with an accidental discovery. It was the turn of the 20th century, specifically the autumn of 1900.
Right around then, yeah.
When Captain Dimitrios Kontos and a crew of intrepid sponge divers from Syme Island were off the rugged coast of the Greek island Antikythera.
They weren't looking for treasure, just sponges. That was their job.
Exactly. But instead, at a chilling depth of 45 meters, or about 148 feet, deep water, they stumbled upon something far more profound: the well-preserved wreck of a large Roman cargo ship lying silently on the seabed for nearly 2 millennia.
And what an extraordinary trove they uncovered. Over the next 2 years, in these really daring dives, often fraught with danger.
Definitely dangerous work back then.
Oh, absolutely. They recovered a staggering collection of treasures. There were magnificent bronze and marble statues, some of the finest examples of ancient Greek sculpture ever found.
Some real masterpieces.
Truly. Alongside these were a vast array of everyday Roman artifacts: exquisite pottery, delicate glassware, intricate jewelry, and a scattering of ancient coins. It was an astonishing haul by any measure, immediately recognized as an archaeological triumph.
Huge news at the time.
Massive. But nestled among these more obvious glittering artifacts was a heavily corroded lump. It appeared to be nothing more than, a nondescript combination of bronze and fragments of wood, seemingly unremarkable, retrieved from the wreckage in 1901.
This lump, despite its eventual earth-shattering significance, went largely unnoticed for the better part of 2 years. And you can hardly blame the museum staff in Athens. They were understandably preoccupied.
Oh, totally. They had tons of statues to piece together.
Yeah.
Literally.
Right. They were dealing with the more glamorous and indeed immensely challenging task of meticulously piecing together the shattered fragments of marble and bronze statues. The lump itself, by the time it reached the surface, had transformed into this complex mineral matrix. It's a tachyte, I think you mentioned.
Yes, a tachyte, a copper chloride mineral. And that process coming out of the cold, deep seawater into the air, it wasn't kind to it.
No, it caused the object to crack and shrink significantly upon its removal. Led to severe deformational changes, making it look like an indistinguishable mess of rock and corroded metal.
Yeah, not exactly screaming ancient computer.
Definitely not shouting, "Hey, I'm a cutting-edge ancient computer," at first glance.
Then, on a truly fateful day, May 17, 1902, the Greek archaeologist Philarios Stais was conducting a routine visit to the National Archaeological Museum. Standard stuff.
Just checking on the finds.
Exactly. And it was during this very visit, as he examined the seemingly inert lump, that he made the discovery that would irrevocably alter the course of archaeological and scientific history. He noticed a gear wheel.
A gear wheel, just embedded in the rock.
Not just a hint of one, but an unmistakably defined gear, clearly embedded within one of the pieces of this seemingly inanimate rock. His cousin, the prominent Greek politician Spiridon Stais, was remarkably with him at the time, witnessing this incredible, quiet moment of revelation.
Wow, what a moment. Stais, with remarkable intuition, initially hypothesized that what he had found might be some form of astronomical clock, a truly insightful guess as it turned out.
Amazingly insightful, yeah.
But, as is often the case with discoveries that challenge prevailing paradigms, most scholars at the time dismissed it outright. They branded it prochronistic, a term specifically meaning ahead of its time.
Basically impossible. Their reasoning was simple, yet profound. Such a complex and precise mechanical device simply could not have been built by the ancient Greeks, given the prevailing understanding of their technological capabilities.
It just didn't fit. It was too advanced, too anomalous to fit into their established historical framework of ancient technology. This initial rejection, this labeling, speaks volumes about how deeply ingrained our perceptions of history can be.
And this very dismissal, this labeling of it as prochronistic, truly raises an important question that echoes through time. How could such astonishingly advanced technology appear so utterly out of place in the historical record?
Right, it's like finding a smartphone in a medieval castle.
Exactly. This initial skepticism caused interest in the device to wane significantly for decades, relegated to a curiosity rather than a focal point of research. That is, until a visionary British science historian named Derek J. DeSolla Price became utterly fascinated by it in 1951. He saw something others had dismissed, a profound puzzle waiting to be solved.
Here's where it really begins to get interesting, because this is where modern technology finally starts to peel back the almost 2,000-year-old layers of this ancient mystery.
The game changes here.
In 1971, Price, alongside the brilliant Greek nuclear physicist Charalampos Karakalos, pioneered the revolutionary use of X-ray and gamma-ray imaging on the then 82 fragments that had been carefully recovered from the mechanism.
Think about that applying medical imaging to archaeology back in the 70s. That was seriously cutting edge.
An absolute game changer. Price then published his groundbreaking findings in a pivotal paper in 1974, which truly reignited scholarly interest, providing the first concrete evidence of its intricate internal workings and beginning to chip away at that stubborn prochronistic label.
These early pioneering investigations by Price and Karakalos laid the crucial groundwork for understanding the device's true nature, moving it from a curiosity to a subject of serious scientific inquiry. Yet, even with these advancements, the mechanism continued to challenge established assumptions about ancient capabilities, proving to be a persistent and tantalizing puzzle.
Still holding on to some secrets.
Definitely. It's worth noting that dedicated, comprehensive searches at the Antikythera wreck site in 2012 and 2015 have continued to yield artifacts, deepening our understanding of the ship and its cargo.
Found anything else from the mechanism itself?
Well, a bronze disc was found during these later expeditions, initially thought by some to be another cogwheel from the mechanism due to its shape, but it was more likely a decoration from a piece of furniture, according to subsequent, more thorough analysis.
Ah, okay. So a bit of red herring.
Seems like it. So far, no more definitive pieces of the mechanism itself have been identified from these later dives, making the existing fragments all the more precious. 2. Unraveling its purpose. What exactly is the Antikythera mechanism?
So, after decades of meticulous study, painstaking imaging, and scholarly debate, what does all this research tell us about what the Antikythera mechanism actually is?
Well, the consensus now is pretty clear. At its core, it is now unequivocally recognized as an ancient Greek hand-powered orrery, a remarkable mechanical model of the solar system.
Right, the clockwork model.
And, crucially, it holds the distinction of being the oldest known analog computer. Think about that for a moment. An analog computer from antiquity.
It still sounds incredible saying it.
Indeed. Its primary and most astonishing function was to predict astronomical positions and eclipses, not just for a few days or weeks, but with a predictive power extending decades, if not centuries, into the future.
That's amazing predictive power for back then.
Unparalleled for its time, demonstrating a profound grasp of astronomical cycles. But what's even more surprising and provides a fascinating link between the abstract world of celestial mechanics and the tangible rhythms of human culture is that it also tracked a 4-year cycle of major athletic games.
Like the ancient Olympic Games.
Akin to those, yes. The major Panhellenic Games. It wasn't just a scientific instrument, it was a societal calendar too. It connected the heavens to, well, sporting events.
Incredible! To visualize this ancient marvel, let's talk about its physical form. The device was originally housed within a beautifully crafted wooden-framed case, approximately 34 centimeters by 18 centimeters by 9 centimeters. That's roughly 13.4 by 7.1 by 3.5 inches.
So about the size of a shoebox, maybe.
Yeah.
Or a large book. Not huge, but packed.
Exactly. When it was initially discovered, it was, as we discussed, a single, heavily encrusted lump. Over time, through the initial handling during recovery and subsequent delicate conservation efforts, this single lump fractured into 3 main fragments.
And now, how many pieces are there?
Today, after extensive, painstaking conservation work that involves everything from chemical baths to micro-excavation, it is recognized as 82 distinct fragments, each a precious puzzle piece.
82 fragments, wow. It's important to understand the distribution of these pieces. Out of those 82, only 4 actually contain visible gears.
Only 4 with gears.
Only 4. However, detailed and often incredibly faint inscriptions are found on many of the other fragments, providing vital linguistic and numerical clues to its operation and purpose.
So the text is just as important.
Absolutely crucial. The largest gear, a truly impressive piece of ancient engineering, measures about 13 centimeters, or roughly 5 inches, in diameter, and remarkably originally had 223 teeth.
223 teeth on one gear.
Precisely cut. All these precious fragments of the mechanism are carefully preserved at the National Archaeological Museum in Athens, displayed alongside various reconstructions and replicas that help visitors visualize how this incredible device might have looked and functioned, bringing the ancient world to life.
A truly significant leap in our understanding of the mechanism came in 2005, ushering in what many call the digital era of Antikythera research.
Yeah, this was huge.
This was when a dedicated international team from Cardiff University, led by the visionary Mike Edmonds, employed cutting-edge computer X-ray tomography and high-resolution scanning techniques. This wasn't just a simple X-ray, this was advanced medical imaging technology repurposed for archaeology.
Like a CT scan for an ancient artifact.
Exactly. This cutting-edge technology allowed them to see inside the crust-encased mechanism in 3 dimensions, revealing its intricate inner workings in unprecedented detail, and, even more remarkably, deciphering the incredibly faint, previously unreadable inscriptions that once covered its outer casing.
It was truly like getting an instruction manual from 2 millennia ago finally brought into the light. These sophisticated scans were revolutionary. They didn't just show us that there were gears, they revealed that the mechanism housed no less than 37 meshing bronze gears.
37 gears.
Minimum. This complex arrangement of gearing allowed it to meticulously follow the movements of the moon and the sun through the zodiac. It could accurately predict eclipses, and perhaps most impressively for its time, it was designed to model the irregular, non-uniform orbit of the moon.
What do you mean by irregular?
Specifically, how the moon's velocity varies between its perigee, when it's closest to Earth and moving fastest, and its apogee, when it's furthest away and moving slowest. This is simple circular motion.
Right, it speeds up and slows down.
Precisely. And this particular nuanced lunar motion was a key focus of the brilliant astronomer Hipparchus of Rhodes in the 2nd century BC, leading many to suggest his direct intellectual involvement, or at least his theories, in the machine's construction.
So maybe Hipparchus designed it? Or inspired it?
That's the strong suspicion. It shows an incredible depth of astronomical knowledge applied mechanically.
And here's another astonishing detail that truly demonstrates the incredible astronomical sophistication embedded within this ancient machine. The inscriptions, which were painstakingly further deciphered and analyzed in 2016 by the Antikythera Mechanism Research Project,
More text revealed.
even revealed specific numbers 462 and 442 connected with the synodic cycles of Venus and Saturn.
The synodic cycle, for our listeners, is the time it takes for a planet to return to the same position relative to the sun as observed from Earth.
Right.
Like from one opposition to the next, for Mars, for example.
Okay, so finding cycles for Venus and Saturn, that's huge, right?
It is. This discovery hints at an even greater astronomical predictive capability than was initially believed, suggesting it wasn't just tracking the sun and moon, but potentially the motions of other classical planets as well. It just keeps getting more complex. 3. The genesis and journey. Where did it come from and how old is it? Moving on to its genesis and timeline, the instrument is widely believed to have been meticulously designed and constructed by Hellenistic scientists, essentially, the intellectual heirs of ancient Greece.
The peak of Greek science, really.
Pretty much. There's been a fascinating and ongoing debate over its exact dating, with various researchers proposing a range of periods. Some initial estimates placed its creation around 87 BC,
Okay, so early 1st century BC.
while others pushed it earlier to between 150 and 100 BC, and some have even suggested as early as 205 BC.
Yeah, that's a big range. Over a century difference.
It is. The wide range speaks to the difficulty of pinpointing its exact moment of creation, given the limited evidence.
What we do know with a higher degree of certainty, though, is the shipwreck itself. The Roman cargo ship that carried the mechanism has been meticulously dated by multiple lines of archaeological evidence, including pottery, coins, and the ship's construction style.
All pointing to roughly the same period.
Right, to approximately 70-60 BC. This provides an absolute terminus post quem. The mechanism had to have been constructed at some point before that date.
It sets a deadline, essentially. It couldn't have been made after the ship sank.
Exactly. It's like finding a 1990s laptop in a ship that sank in 1850. You immediately know the ship's sinking date establishes a clear chronological marker for the laptop's production. The mechanism's presence on a ship from the 1st century BC clearly places its creation much earlier.
Indeed. Newer, highly refined research from 2022, which delved into the astronomical alignments and calendar settings encoded in the mechanism, proposed that its initial calibration date.
Not when it was built, but when it was sort of set.
Exactly. The precise astronomical epoch from which its cycles were set to begin could have been as specific as December 23, 178 BC.
That's specific. Wow.
That's specific, according to their calculations. Other experts, however, leaning on different astronomical interpretations, suggest 204 BC as a more likely calibration date.
So still some debate even on the calibration.
Still some debate. Regardless of the precise year, what's truly striking and profoundly undeniable is that machines of similar mechanical complexity with multiple intricate gears designed for calculation simply did not reappear in Western Europe until the 14th century.
Over 1,000 years later.
Over 1,000 years. This truly makes the Antikythera mechanism an isolated and anomalous marvel, a solitary witness to a lost technological golden age.
So who possessed the unimaginable genius to build this incredibly advanced machine? The sheer quality and complexity of its manufacture strongly suggests that it couldn't have been a singular one-off invention, a mere fluke.
No way. This wasn't beginner's work.
This level of precision and sophisticated design implies the existence of undiscovered predecessors, a lineage of advanced mechanical knowledge, and a workshop of master craftsmen whose brilliant work has sadly been lost to us through the millennia.
Its construction relied heavily on Greek astronomical and mathematical theories that were already highly developed by the 2nd century BC, demonstrating that the intellectual groundwork was certainly there. The theory was ready.
His knowledge existed.
In 2008, the ongoing Antikythera mechanism research project put forward a compelling theory suggesting a Corinthian origin. This was based on their painstaking identification of the Metonic spiral calendar on the device as being specifically Corinthian.
Because of the month names.
Exactly, the unique month names used. This led them to speculate it might have come from Corinth itself, a major Greek city-state, or one of its numerous colonies spread across northwest Greece or Sicily.
Like maybe Syracuse, Archimedes' home.
For a time, Syracuse, the famous home of Archimedes and a significant Corinthian colony, was considered a strong contender, sparking exciting speculation about a direct connection with Archimedes' legendary school of thought.
That would be amazing.
It would. However, later, more granular research in 2017 more specifically demonstrated that while the calendar was undeniably Corinthian, it could not have been from Syracuse itself due to slight calendar variations, refining but not entirely dismissing that connection. So close, but maybe not Syracuse itself.
Okay, so Corinth or a colony, but probably not Syracuse. What other ideas are there?
Another intriguing theory links its origin to Pergamon, an ancient Greek city in modern-day Turkey, renowned for its magnificent library, which was second only to Alexandria in intellectual importance during the Hellenistic period.
A major center of learning.
Absolutely. This idea is partly based on some specific coins found at the wreck site by the legendary Jacques Cousteau during his pioneering underwater expeditions in the 1970s. It paints a picture of a major intellectual and cultural hub being the likely birthplace of such a sophisticated device, suggesting it was part of a larger tradition of scientific innovation.
Makes sense. High-tech needs a high-tech environment.
However, many researchers, myself included, tend to point most strongly to the island of Rhodes as the most probable origin. This theory is supported by several compelling pieces of converging evidence.
Okay, why Rhodes?
Firstly, the ship carrying the mechanism also contained vases in the distinct Rhodian style, suggesting a connection to the island's trade. Secondly, Rose itself was not just a bustling major trading port, but significantly a renowned center for both astronomy and mechanical engineering.
Famous for the Colossus, right? But also science.
Exactly. Famous for its colossal statue and its intellectual prowess. Crucially, it was also home to the brilliant astronomer Hipparchus, who was active from about 140 to 120 BC.
Ah, Hipparchus again?
Yes. The mechanism notably incorporates Hipparchus's sophisticated theory for linear motion, which accounts for the moon's varying speed in its elliptical orbit. This strongly suggests he may have had a direct hand in its design, or at least his cutting-edge theories were central to its calculations.
The connection seems really strong there.
It does. Furthermore, the astronomical events meticulously inscribed on the mechanism's parapegma, essentially an ancient almanac that tracked the heliacal risings and settings of stars, work best for latitudes that closely match those of Rhodes, providing a compelling geographical link.
So the sky it describes looks like the sky from Rhodes.
Pretty much, yeah, it fits best.
Adding another fascinating layer to the dating debate, a 2014 study argued for a new dating of the mechanism to around 200 BC. This was based on correlating the Saros-style startup date with the new moon of April 28, 205 BC.
Pushing it even earlier.
Right. What's particularly interesting about this theory is its suggestion that Babylonian arithmetic prediction methods actually fit better with the device's predictive models than the more traditional Greek trigonometric styles.
So maybe Babylonian math influenced Greek engineering.
It hints at a...
Exactly. This suggests that the final construction and specific calibration of this particular mechanism might have occurred only a generation or so before the shipwreck itself, perhaps adapting a sophisticated general design for specific regional patrons' needs. Someone in Epirus wanted one, maybe.
Tailor-made tech. Fascinating. 4. A glimpse inside. Design and core mechanics. Now, let's take a closer look at what survived of this incredible machine, how its fragments have been pieced together, and what they reveal about its inner workings. The mechanism, as we've mentioned, came out of the sea as a single, heavily encrusted piece, almost indistinguishable.
Just a lump of corrosion.
But soon after, likely due to the shock of exposure to air and handling, it fractured into 3 major pieces. Through subsequent careful cleaning, meticulous handling, and later discoveries from additional dives at the wreck site, we now have 82 known fragments, each a vital clue in this grand historical puzzle.
It's a testament to the incredible fragility of such an ancient relic and the immense dedication of conservators. 82 pieces to work with.
Of these 82 fragments, it's worth noting that only 7 are considered mechanically significant.
7 key pieces. These are the ones that contain the bulk of the mechanism's internal structure and its crucial, deeply inscribed text.
So the gears and the main text are on just 7 fragments.
Largely, yes. Another 16 smaller pieces, while not central to the gearing, hold partial inscriptions, which have still provided vital clues for its reconstruction. For example, fragment 19 notably contains a clear inscription reading 0.76 years, a direct reference to the Ecliptic cycle, a key astronomical period the mechanism was designed to track.
Even tiny fragments hold clues.
Invaluable clues. This fragmentary textual evidence has been invaluable in understanding the machine's intended functions.
You might be wondering, how did this thing even work? How did someone operate a device that was, in essence, a 2,000-year-old computer?
Yeah, how do you use it?
Well, the mechanism was operated by a small, now lost, hand crank. This crank was ingenious in its simplicity and effectiveness. It linked via a crown gear, a type of gear with teeth around its edge like a crown.
Right, a right-angle drive, basically.
To the largest gear we mentioned earlier, the impressive 4-spoked gear, known as B1, positioned prominently on the front of the mechanism.
Turning that hand crank would simultaneously move the date pointer on the front dial, allowing the operator to set it precisely to the correct Egyptian calendar day.
So you set the date first.
Seems so. It's important to understand that the year itself wasn't directly selectable on the mechanism. So the operator would have needed prior knowledge of the current year, or perhaps consulted external Babylonian ephemeris tables, which were widely available at the time, using the various calendar cycle indicators on the back of the device to ensure accurate alignment.
So it wasn't plug and play, you needed to know stuff.
Definitely. This interaction highlights that while incredibly advanced, it still required an astronomer or knowledgeable operator to set it correctly for a given year, as most of the calendar cycles weren't perfectly synchronous with a single specific year.
The genius in its operation, the true aha moment, is truly astounding. A single full rotation of that small hand crank would precisely move the date pointer approximately 78 days, allowing for incredibly fine and accurate setting of the mechanism.
So you could fine-tune the date easily.
Right. But here's the real magic. This single, simple crank movement simultaneously caused all the interlocked gears within the mechanism to rotate in perfect synchronicity.
Everything moves at once.
This meant it was continuously dynamically calculating the sun and moon's positions, displaying the current moon phase, accurately predicting upcoming eclipses, and tracking various calendar cycles. And, as we'll discuss, it's even speculated that it might have calculated the locations of the then-known planets as well.
All from that one simple turn of a crank. Incredible integration.
Absolutely.
Additionally, while much of its operation was automated once set, the operator did have a small, crucial manual task to perform. They had to manage the spiral dial pointers on the two large rear dials.
The spiral dials,
Yeah.
what did they have to do?
As a pointer reached the very end of a spiral track, like a stylus tracing a groove, its follower, the small pin that physically traced the spiral had to be manually lifted and moved to the other end of the spiral.
To start the next loop of the spiral.
Precisely. This allowed for the continuous tracking of the cycle as it transitioned from one full rotation of the spiral to the next, demonstrating a fascinating blend of complex, automated calculation and necessary human interaction to maintain its continuous operation. The detailed faces, front and rear dials.
Let's delve even deeper into the detailed faces of the mechanism, starting with the front, which was clearly designed to map the visible sky. The front dial features two concentric circular scales, one inside the other.
Two rings.
The inner scale precisely marks the Greek zodiac signs, divided into meticulous 30-degree sectors, a convention that aligns perfectly with ancient Babylonian astronomical customs.
Standard zodiac, yeah. Borrowed from the Babylonians.
The outer scale, a movable ring, was for many years presumed to be a standard 365-day Egyptian solar calendar, which was commonly used in the Hellenistic period.
That was the assumption for a long time.
However, recent groundbreaking research from 2020 by Budiselik et al., and further corroborating studies in 2024 by Wone and Bailey and Mellon and Dickens have provided strong statistical evidence for 354 intervals on this outer ring rather than 365.
354 days, that changes things.
Right. This strongly suggests it actually represents a lunar calendar, aligning with 354 days in a lunar year. If this is correct, it implies it might be the first known example of the Egyptian civil-based lunar calendar, a sophisticated concept proposed by Richard Anthony Parker in 1950.
So maybe it tracked the moon's phases day by day, not the sun's position in a solar year.
That seems to be the new thinking. If it was indeed originally a 365-day calendar, it would predate the Julian calendar reform by over a century, which standardized a 365.25-day year.
And they knew about the quarter day, even back then, roughly.
Right. However, it's worth noting that even before the Julian calendar, Sophic and Ecliptic cycles in Greek astronomy had already pointed to a year length closer to 365.25 days. In this scenario, the outer dial could have been manually moved against the inner zodiac dial to compensate for leap days.
You'd nudge it every 4 years or so.
Exactly. But if the newer evidence pointing to a 354-day lunar calendar is correct, its primary purpose would have been to clearly indicate successive lunations and aid in interpreting the lunar phase pointer, as well as the Metonic and Saros dials on the back. It would have effectively provided a day-to-day indicator of lunar phases within a consistent lunar year framework.
Makes sense? A daily lunar guide. This front dial also meticulously marked the sun's position on the ecliptic, the apparent path of the sun through the sky. Two primary pointers specifically indicated celestial bodies on the ecliptic, a lunar pointer and a mean sun pointer.
Okay, pointers for sun and moon.
What's truly remarkable, and a testament to the engineering genius, is that the lunar pointer was not a simple mean indicator implying uniform movement. Instead, it ingeniously approximated the moon's acceleration and deceleration in its elliptical orbit through the use of epicyclic gearing, a complex system of gears within gears.
Gears riding on other gears, right?
Yeah.
To simulate that faster, slower movement.
Exactly. This is the earliest known use of such a system to model non-uniform motion, far predating its common use in later European clockwork. This level of mechanical modeling for astronomical phenomena is truly astonishing.
And here's a surprising fact that truly underlines the depth of sophistication in this ancient machine. It also tracked the precession of the moon's elliptical orbit, an incredibly subtle astronomical phenomenon where the orientation of the moon's elliptical path slowly rotates,
The whole ellipse turns slowly in space.
completing a cycle in approximately 8.88 years. That's a deep level of observational detail. Furthermore, the brilliant mechanical engineer Michael Wright, in his reconstructions, demonstrated a truly elegant mechanism for displaying the lunar phase.
How did that work?
A small ball, half white and half black, was ingeniously embedded on the lunar pointer. This ball would rotate to visually show the various phases of the moon from new to first quarter to full to third quarter and back again.
All driven by a clever differential gear that summed or differenced the angular inputs of the sun and moon pointers. It was a complete visual display of the moon's monthly cycle. Just amazing.
I feel cool.
The zodiac dial on the front face includes the precise Greek inscriptions for each of the zodiac signs, such as Krios for Aries and Tauros for Taurus, showing meticulous attention to detail. It also features single characters at specific points on the dial, which are key to a parapegma.
A parapegma, like an almanac.
Exactly, an ancient almanac, meticulously inscribed both above and beneath the dials. These inscriptions mark the precise longitudes on the ecliptic for specific, prominent stars like the Hyades, Pleiades, Lyra, Altair, and Arcturus, and also precisely mark the critical astronomical points of the solstices and equinoxes.
So it told you when certain stars would rise or set alongside the calendar.
Yes, it demonstrates how deeply integrated celestial observation and the calendar were with the practical functions of the device, making it a comprehensive guide to the heavens.
Now, let's metaphorically flip the mechanism over, because the rear face is equally astonishing, perhaps even more so, as it's dedicated to tracking even more complex astronomical cycles and, remarkably, ancient athletic games.
Yeah, the back is where a lot of the really complex cycles are shown.
Here, nestled on the back plate, you find 5 more dials. There are 2 large, prominent displays, the Metonic and Saros dials, and 3 smaller but equally important indicators. The Games dial, which was formerly known as the Olympiad dial, before more precise decipherments.
Right, we know more about it now.
Along with the Callippic and the Exoligmos dials, it's an intricate web of temporal calculation.
The Metonic dial, which is the main upper dial on the rear, covers a period of 235 synodic months. For our listeners, a synodic month is the time it takes for the moon to complete one cycle of phases, as observed from Earth, essentially. The periods from one new moon to the next.
The time between full moons, roughly?
Roughly, yes. Yeah. This period of 235 synodic months is incredibly precise, almost exactly 19 tropical years, accurate to within less than 13 1/millionths of a year.
Wow. So 19 years of moon cycles.
Which makes it an incredibly convenient and accurate interval for converting between lunar and solar calendars, a significant challenge for ancient astronomers trying to synchronize agricultural cycles with religious festivals. The Metonic dial itself displays these 235 months in 5 spiral rotations, with a follower on the pointer that meticulously tracks which layer of the spiral the current month falls on.
5 loops in the spiral.
Right. It points to the specific synodic month, counted from new moon to new moon, and fascinatingly, the cells on the dial contain Corinthian month names, such as Phonikaios and Mechanius, the latter of which remarkably means mechanic, possibly referring to Zeus the inventor, or perhaps the ingenuity of the device itself.
Mechanius, the mechanic month, that's great. And based on these very specific Corinthian month names, and the fact that the Games dial also makes a point of mentioning the relatively minor Norna Games of Dodona, a local festival, not one of the major Pan-Hellenic games.
The local connection again.
Some researchers argue that the calendar displayed on the mechanism is in fact an Epirote calendar. Epirus was a region in northwestern Greece. It's theorized that it might have been adopted from a Corinthian colony in Epirus, perhaps Ambracia, which had strong cultural ties.
So maybe built for someone in Epirus, using their local calendar variations.
Seems plausible. The first month, Phonikaios, ideally coincided with the autumn equinox, suggesting a possible startup date for the calendar near August 23, 205 BC. This shows the incredible regional specificity, suggesting a custom-made device.
The Games dial, which is the right secondary upper dial on the rear, is particularly unique because its pointer travels in an anti-clockwise direction as time advances, unlike most other pointers on the mechanism.
Goes backwards. Why?
Not sure why backwards, but it does. This dial is intricately divided into 4 sectors, and each one is clearly inscribed with a year indicator, like Lael, Lay, for years 1, 2, 3, and 4 of a cycle. More importantly, it shows the names of 2 major Pan-Hellenic games, the crown games of Isthmia, Olympia, Nemea, and Pythia,
The big ones.
alongside 2 lesser, more local games, the Nea, held at Dodona, and the Helia of Rhodes. This is truly fascinating as it directly links the complex astronomical prediction of the device to the everyday cultural and athletic life of the ancient Greeks, demonstrating its practical application beyond pure science, integrating it into the social fabric of the time.
It wasn't just for astronomers, it was for knowing when the games were on. Then there's the Saros dial, which is the main lower spiral on the rear. The Saros cycle is famously about 18 years and 1/3 of a day long, or precisely 223 synodic months.
The key eclipse prediction cycle.
This is the crucial period after which solar and lunar eclipses repeat in a very similar pattern, allowing for their prediction. The mechanism's Saros dial doesn't just predict the month, it specifies the occurrence of 38 lunar and 27 solar eclipses, with intricate glyphs in 51 of its 223 cells indicating the specific eclipse.
Glyphs, like little symbols.
Exactly. These glyphs even provide startling precision, indicating the day and, remarkably, the hour, using abbreviations like sigma for moon, indicating lunar eclipse, and eta for sun, indicating solar eclipse. It's like a predictive eclipse almanac right there on the device.
Predicting the hour of an eclipse 2,000 years ago. Incredible. The X-Litmos dial, the secondary lower dial, takes this predictive capability even further, refining it to an astonishing degree. It represents a 54-year triple Saros cycle.
Triple Saros? Why triple?
The reason this cycle is so important is because, as you mentioned, the Saros cycle is approximately 8 hours longer than an integer number of days. That third of a day adds up.
So the eclipse time shifts by 8 hours each cycle.
Right. So if an eclipse occurs at noon on day 1 of a Saros cycle, the next eclipse in that cycle would occur at roughly 8 p.m., and the one after that at 4 a.m. This seemingly small offset accumulates. The X-Litmos cycle brilliantly solves this by tripling the Saros cycle after exactly 19,756 days, or 54 years. It brings the counting back to an integral number of days, meaning the eclipse will occur at the same time of day again.
Clever, so it corrects for that 8-hour shift over 54 years.
Precisely. The labels on its 3 divisions blank, or 0, H, eta for 8, and is, iota sigma for 16, indicate exactly how many hours must be added to the Saros dial's eclipse times for precise calculation, ensuring that the prediction accounts for that critical 1/3 day offset. It's an incredibly clever solution to a very tricky problem.
As for the user interface, beyond the intricate dials themselves, the beautifully crafted wooden casing of the mechanism had both front and back doors, which would have protected the delicate bronze gears inside. Crucially, the back door didn't just provide access.
It was the manual.
It essentially served as the device's comprehensive instruction manual.
Indeed. Inscriptions found on the fragments of this back door clearly detail the key astronomical cycles the device was built to track. For instance, one remarkable fragment directly states 76 years, 19 years, referring to the Callipic and Metonic cycles respectively, which were fundamental to Greek astronomy for synchronizing solar and lunar calendars.
Just written right there.
Plain as day. Well, think Bronze Day. Another inscription explicitly mentions 223 for the Saros cycle, confirming the number of synodic months that define it. And yet another, on the spiral subdivisions 235, directly refers to the Metonic dial structure. These inscriptions are invaluable. They provide direct, unambiguous insights into the mind of its creators, confirming the cycles they intended the mechanism to track and display, almost like a user's guide etched in bronze. 5. The heart of the machine. Gearing and complexity.
Here's where it really starts to blow your mind. The level of miniaturization and the sheer complexity of the Antikythera mechanism's parts are absolutely astounding.
Truly remarkable engineering.
In fact, they are often compared to the sophistication of astronomical clocks that didn't appear in Europe until the 14th century, over 1,000 years later. It has at least 30 gears in its known fragments, a truly remarkable testament to the advanced engineering capabilities of ancient Greece.
At least 37 confirmed, probably more originally. To put it simply, this was technology that should not have existed when it did, based on what we thought we knew.
Exactly.
And the gear teeth themselves are a marvel of ancient craftsmanship, demonstrating astonishing precision for a handmade artifact. They are in the distinctive form of equilateral triangles.
Not like modern clock gears.
No, not the curved, involute shape we use now.
Yeah.
These were triangular, indicating they were most likely meticulously filed and shaped by hand from a bronze blank, rather than being cast or machine cut. They exhibit an astonishingly uniform average circular pitch of 1.6 millimeters. That's the spacing between the teeth.
Tiny teeth.
Very small and precise, with an average wheel thickness of 1.4 millimeters and an average air gap of 1.2 millimeters between the meshing gears. This consistency speaks to incredible skill. Thanks to modern imaging and X-ray tomography technology, we now know the precise number of teeth and the exact size of the gears in the known fragments. which has allowed for highly accurate digital and physical replication of the mechanism's basic operation in modern models.
Despite this incredible detail and our growing understanding, one major question still remains a subject of intense, passionate debate among researchers. Did the mechanism have specific indicators for all 5 planets known to the ancient Greeks? Mercury, Venus, Mars, Jupiter, and Saturn? Or only for the Sun and Moon?
Ah, yes, the great planet debate. The challenge lies in the physical evidence. No explicit gearing for such a comprehensive planetary display explicitly survives among the known fragments of the mechanism.
So no leftover planet gears found yet?
Not definitively identified as such. Furthermore, all the known gears in the main mechanism are otherwise accounted for in the Sun-Moon eclipse calendar calculations. However, there is one intriguing exception that fuels the debate. Fragment D.
Fragment D, what's special about it?
It's a small, quasi-circular constriction. Contains a 63-toothed gear. Xenophon Musas, a prominent researcher, suggests this fragment might contain an inner gear inside a hollow gear, cleverly designed to reproduce the complex epicyclical motion for Jupiter.
A gear within a gear for Jupiter.
That's his theory. Other theories propose it's related to the Sun's anomalous motion. It's a key piece of the puzzle, but its exact function remains elusive, leaving room for both excitement and continued investigation.
It's important to note here for a moment that whether the positions of celestial bodies were computed using a heliocentric, meaning sun-centered, or a geocentric, earth-centered view of the solar system is actually irrelevant to the mechanism's ability to accurately predict apparent positions within its inherent error factors.
Right. It's about predicting what you see from Earth, regardless of the underlying cosmic model.
The ancient Greeks, like Ptolemy much later, knew how to model the appearance of planetary motion from Earth, using complex systems of epicycles and deferents. In fact, the geocentric epicyclic solar system model of Ptolemy, which was developed hundreds of years later, around 160 AD,
way after the mechanism,
actually used even more complex epicycles to become even more accurate at predicting observed planetary positions than Copernicus's initial, simpler heliocentric model, until Kepler finally introduced the concept of true elliptical orbits in the early 17th century.
Accuracy of prediction was the goal, not necessarily physical reality as we know it now. The space observed behind the mean sun gear, even after meticulously accounting for all the known components and their proposed functions, strongly suggests that there were indeed missing components.
A gap in the machine.
Yeah, physical space where more gears could have fit, perhaps gearing for planets or other complex motions. This critical void has naturally led to numerous reconstruction efforts over the years, each building on the last, starting with Derek J. DeSola Price's initial simple model in the 1970s, which served as a crucial first step in deciphering its complexity.
Then, in 2002, Michael Wright achieved a significant breakthrough. He built the very first workable physical model of the mechanism, bringing it to life for the first time in millennia.
Wright's model was groundbreaking.
His reconstruction daringly added pointers not just for a true sun, accounting for the sun's apparent elliptical anomaly, meaning its slight speed variation throughout the year, but also for all 5 classical planets.
He went all in on the planets.
He did. He hypothesized that the mechanism included sophisticated adjustments for solar anomaly, demonstrating a deeper understanding of orbital mechanics than previously attributed to the Greeks of that era. It was a bold claim and a masterful piece of reverse engineering.
Following Wright's pioneering work, Evans, Carman, and Thorndike proposed a different, equally compelling solution in 2010. Their model focused on what they observed as irregular spacing of inscriptions on the front dial.
The text spacing, how did that help?
They interpreted it as suggesting an off-center sun indicator. This design, if true, would dramatically simplify the mechanism by removing the need for explicit solar anomaly simulation in the gearing. Crucially, it would also allow for simpler planetary dials that showed key events in a planet's cycle, such as its retrograde motion or conjunctions, rather than predicting precise, continuous positions.
So showing when something happened, not exactly where the planet was all the time.
Exactly. Their model also offered an ingenious way to account for the previously unexplained 63-toothed gear in Fragment D, suggesting it was part of a simplified planetary train.
Okay, different take. And then in 2012, Tony Fruth and Alexander Jones, key members of the Antikythera Mechanism Research Project, published a new and highly influential proposal that gained widespread acceptance.
Fruth and Jones, yeah, their work is central now.
They offered what they described as a compact and feasible solution for incorporating full planetary indication into the mechanism. Their meticulously detailed design involved an impressive 8 coaxial spindles, no less than 54 gears, and 3 clever slotted bars to drive the 6 new pointers for the planets and a separate true sun pointer.
A really complex, layered system.
They even went so far as to suggest that the pointers themselves might have featured small identifying stones for each planet based on descriptions from ancient papyri. Golden for the sun, silver for the moon, obsidian for Saturn, reddish onyx for Mars, lapis lazuli for Venus, turquoise for Mercury, and a whitish crystalline stone for Jupiter.
Wow, that really paints a vivid, tangible picture of what this machine might have looked like in full operation. It raises an important question that's at the heart of the ongoing research. Which of these models is correct, or at least the most accurate representation of the original?
Yeah, who got it right?
Well, the answer is that ongoing research continues to refine our understanding, with new discoveries constantly shaping the models. In 2016, for instance, new CT scans, even more powerful than before, revealed specific numbers, 462 and 442, hidden within the inscriptions. These numbers were found to relate to the precise synodic cycles of Venus and Saturn, respectively.
The Venus and Saturn numbers again.
Yes. This indicated that the mechanism was capable of even higher accuracy for these planets than previously thought, potentially accommodating their complex motions with startling precision. Based on these new insights, the Antikythera Mechanism Research Project in 2018 proposed further gearing changes and refinements to previous reconstructions, adapting them to the latest epigraphic evidence.
So the models keep evolving as we learn more, and most recently, in March 2021, the UCL Antikythera research team, still brilliantly led by Tony Freeth, published what they believe is a truly groundbreaking new proposed reconstruction.
The latest big publication.
They claimed that their comprehensive model was compatible with all known data, every inscription, every gear fragment, every piece of evidence meticulously accounted for. They ingeniously found ways for gears to be shared among different planetary gear trains by using rational approximations for the synodic cycles that have remarkably small prime factors, specifically highlighting the factors 7 and 17 as being used for more than one planet.
That's really elegant sharing gears between planets, very efficient design.
It suggests a profound mathematical insight. They even produced a fascinating video explaining this complex discovery, truly demonstrating how all the intricate pieces finally fit together in a coherent, functional system.
While the conceptual design and theoretical sophistication of the Antikythera mechanism were undeniably brilliant, even Freeth and Jones's meticulously simulated mechanism reveals some fascinating limitations. For example, their simulated Mars pointer.
Mars is always tricky, isn't it, with its big loops?
It is. Their Mars pointer, despite the incredible engineering, could still be off by as much as 38 degrees in some specific cases, particularly at the nodal points of its complex retrograde motion, where it appears to move backwards in the sky from Earth's perspective.
38 degrees is quite a lot.
It is. But this wasn't a flaw in the mechanism's construction or the accuracy of its gears, but rather a fundamental limitation of the Greek astronomical theories of the time, which, for all their brilliance, didn't yet fully grasp the true elliptical nature of planetary orbits, which Kepler would only uncover millennia later.
That's a crucial point. The ultimate accuracy of such a device, in terms of truly predictive celestial mechanics, couldn't have been significantly improved until Ptolemy's Almagest was published around 160 AD, which introduced the concept of the equant.
Another theoretical tool to improve geocentric models.
Providing a more accurate geocentric model. And it certainly couldn't reach its full potential until Kepler's groundbreaking laws of planetary motion were established in the early 17th century, finally describing and proving elliptical orbits. The ancient Greeks simply didn't have that fundamental piece of the puzzle yet.
This raises an important question, though. What about the mechanical accuracy, as opposed to the theoretical accuracy? Freeth and Jones noted that the inherent looseness in the mechanism—
The play between the gears.
Exactly. Given its hand-built gears with their triangular teeth, which aren't as precise as modern involute gears, and the inevitable friction in the bearing surfaces, would likely have overwhelmed many of the subtle, precise corrections built into the theoretical design.
So the theory was maybe smarter than the physical execution could handle.
Possibly. In fact, some cutting-edge computer simulations from 2025, which have taken into account the exact shape of the gear teeth and material properties, have even suggested that the cumulative friction and play in the system would have caused the mechanism to jam and stop working after approximately 4 months of continuous operation.
4 months? So it might not have worked for very long.
That's what some simulations suggest. Hard to know for sure, but it points to potential mechanical limitations.
So despite being lauded as a conception of pure genius and one of the great wonders of the ancient world, the mechanical reality suggests it didn't really work very well for extended, continuous periods.
Maybe not perfectly, or not for long stretches without maintenance, perhaps.
But here's the kicker, the truly mind-blowing part that rewrites history. The underlying concept and the advanced mechanical technology it employed, things like using a sophisticated pin-and-slot epicyclic mechanism to accurately model elliptical paths in retrograde motion,
That pin-and-slot mechanism is ingenious.
actually predated the first known mechanical clocks and complex gear devices in medieval Europe by over 1,000 years. The ideas were simply millennia ahead of their time, even if the physical execution had its limitations.
This truly highlights that the Greeks, with brilliant mathematicians like Archimedes developing concepts such as the approximate value of pi and making significant steps towards calculus, clearly possessed the profound mathematical knowledge necessary to model complex motions like elliptical paths.
They could do the math.
They could. This was true even if they didn't fully grasp the true elliptical shape of the orbits themselves, demonstrating an incredible leap of abstraction from observed celestial phenomena to a sophisticated mechanical representation. It's an engineering marvel born of deep theoretical insight. 6. Echoes through time. Similar devices and lasting legacy.
Given its astonishing sophistication and the evident level of craftsmanship, the Antikythera mechanism couldn't possibly have been a unique, one-off invention, a singular stroke of genius in isolation.
Highly unlikely. You don't just invent something this complex out of the blue.
The level of refinement, the precision of its gears, and the sheer complexity of its design strongly suggest that it required expertise built over several generations, implying a rich, albeit largely lost, tradition of advanced mechanical engineering within the Hellenistic world. It begs the question, how many more of these machines once existed?
That's the sad truth. Artifacts like the Antikythera mechanism were commonly made of bronze. This metal, for all its utility, was highly valuable and easily recyclable, especially in times of conflict or economic hardship.
Melted down for swords or coins.
Exactly. So it's highly probable that such complex devices, once their initial utility waned or their owners died, were simply melted down for their raw material. This explains, at least in part, why so few such advanced mechanisms survive today, leaving us with what amounts to a lost history, a technological dark age, for which the Antikythera mechanism is a solitary, shining witness of truly brilliant ancient engineering.
Fascinatingly, despite the archaeological silence, ancient literature does indeed mention devices that sound remarkably similar to the Antikythera mechanism. The renowned Roman philosopher Cicero.
Cicero wrote about them.
He did. In his influential work, De Republica, written between 54 and 51 BC, offers tantalizing descriptions of two such machines. He recounts that these devices were built by none other than the legendary Archimedes, the brilliant mathematician and engineer from Syracuse.
Archimedes again.
These machines were said to predict the precise movements of the sun, the moon, and even the 5 planets known at the time. They were famously brought to Rome by the Roman general Marcus Claudius Marcellus after Archimedes' tragic death at the siege of Syracuse in 212 BC, well before the Antikythera shipwreck.
So Archimedes definitely built similar things, according to Cicero. Cicero recounts in vivid detail that one of these Archimedean machines was kept as a cherished family heirloom by the Marcellus family. He specifically describes Gaius Sulpicius Gallus, a learned Roman consul and astronomer, giving a learned explanation and a working demonstration of the device.
Someone actually saw it work and described it.
Yes. Gallus vividly described how it accurately showed the relationship of the moon with the sun, and even demonstrated the complex phenomena of solar and lunar eclipses. It's an incredibly detailed account that aligns remarkably with the core functions of the Antikythera mechanism, strongly supporting the idea that such devices were not only conceived, but built in the ancient world.
Adding to this literary evidence, Pappus of Alexandria, a significant Greek mathematician who lived from 290 to about 350 AD, stated explicitly that Archimedes had even written a now-lost manuscript titled On Sphere Making.
A handbook for building these things, if only we had that.
Imagine! This treatise would have detailed the theoretical and practical construction of such planetary models, providing the instruction manual for building such complex orreries. And here's an interesting detail about Archimedes' other inventions. His famous odometer, a device for measuring distance traveled, described by Roman writers like Vitruvius and Heron of Alexandria.
A distance counter.
It only functioned correctly when it's depicted square-toothed gears were replaced with angled or triangular gears, Precisely the kind of triangular angled gears meticulously found and measured in the Antikythera mechanism.
So the same advanced gear type shows up in descriptions of Archimedes' work. Interesting link.
It suggests a shared, highly advanced understanding of sophisticated gearing techniques across different ancient Greek workshops.
However, it's highly unlikely that any of these specific machines mentioned in ancient texts, even those attributed to Archimedes, were the Antikythera mechanism itself.
Why not?
This is primarily because Archimedes' devices, as described by Cicero, were located in Rome at least 30 years after the estimated date of the shipwreck, making it chronologically impossible.
The timing is wrong.
Exactly. So, while not the exact device, these ancient accounts powerfully support the idea that such complex astronomical machines existed in the ancient world were not unique to Antikythera, and were part of a wider, albeit mostly lost, tradition of mechanical genius.
So, what does this all mean for the broader history of technology? The very existence of the Antikythera mechanism profoundly supports the idea of a vibrant, sophisticated ancient Greek tradition of complex mechanical technology that flourished for centuries.
It wasn't a fluke, it was a tradition.
And perhaps even more importantly, this technology was later, at least in part, transmitted to subsequent civilizations, acting as a crucial bridge of knowledge across time and cultures.
We can clearly see echoes of this advanced knowledge in the Byzantine Empire, where fragments of geared calendars from the 5th or 6th century have been discovered, likely used to assist in time-telling for religious purposes or scholarly pursuits.
So the knowledge didn't completely vanish.
No, it seems bits and pieces survived. The transmission then continues prominently into the Islamic world. Highly influential texts like Banu Musa's 9th century Kitab al-Hiyal or Book of Ingenious Devices described over 100 mechanical devices, including automata and water clocks, showcasing incredible ingenuity building upon ancient principles.
Wow, the Book of Ingenious Devices.
Sounds great, doesn't it? A geared calendar, remarkably similar to the Byzantine one, was described by the polymath al-Biruni around 1000 AD, further demonstrating the continuity of this knowledge. And a surviving 13th century astrolabe from Islamic Spain actually contains a similar clockwork device for calendar calculations.
So the Islamic Golden Age carried this torch.
Definitely played a huge role. This rich medieval technology, itself deeply rooted in ancient knowledge, may then have been transmitted to Europe, significantly contributing to the development of mechanical clocks there, which truly began to emerge in the 14th century.
So the Antikythera is kind of the ancestor of the European clock tower.
In a way, yes, a very distant ancestor, but the lineage of complex gearing seems to connect. The influence wasn't just westward. In 11th century China, the brilliant polymath Su Song constructed an incredible mechanical clock tower that meticulously tracked celestial positions, incorporating sophisticated escapement mechanisms and astronomical models.
China too. Amazing.
The influence of this ancient Greek mechanical genius, as evidenced by the Antikythera mechanism, is undeniably global and spans centuries, connecting disparate cultures and time periods through the enduring thread of scientific and engineering innovation. 7. The Antikythera mechanism in the modern world.
Today, the Antikythera mechanism continues to captivate the imagination of scientists, historians, and the public alike. It is, without dispute, the undisputed star of the Antikythera shipwreck exhibition at the National Archaeological Museum in Athens.
The crown jewel of the museum, really.
Drawing visitors from around the world who stand in awe of its complexity.
Indeed. Beyond its original home, numerous reconstructions and replicas exist worldwide, allowing people to interact with and truly comprehend this ancient marvel. These range from the early conceptual models by Ioannis Theophanides and Dergisola Price, which were crucial for understanding its function,
The pioneering models?
to more modern, incredibly intricate recreations found at prestigious institutions like the American Computer Museum in Montana, the Children's Museum of Manhattan, the Katsanis Museum of Ancient Greek Technology in Athens, and the Musée des Arts et Métiers in Paris. Each one helps tell its story.
So you can see versions of it all over. And in a truly grand gesture that speaks to its enduring, awe-inspiring nature, a monumental 10x scale replica was recently built and inaugurated at the University of Sonora in Hermosillo, Mexico in February 2024.
10 times bigger.
Wow. It's reportedly the only fully functional one of its colossal size, standing as a new, impressive, and very public testament to ancient Greek genius, visible from afar and inspiring a new generation.
The mechanism has also permeated popular culture, inspiring awe and curiosity in a wider global audience. It's been prominently featured in compelling documentaries, such as National Geographic's Star Clock BC and the BBC 4 Nova special, The 2,000-Year-Old Computer, bringing its incredible story to millions worldwide and sparking countless conversations about ancient capabilities.
And if you're a fan of creative engineering, you can even find a fully functioning Lego reconstruction built by hobbyist Andy Carroll, a testament to how its ingenious design inspires even contemporary, playful recreations.
A Lego Antikythera mechanism, that's fantastic.
And for movie buffs, a fictionalized, albeit highly dramatized, version of what they called Archimedes' Dial was a central plot point in the 2023 film Indiana Jones and the Dial of Destiny.
Ah, yes, Indy's adventure with it.
Of course, the movie took some enjoyable liberties with its function. For example, the humorous detail of it not accounting for continental drift, which certainly wouldn't have been a problem for the original.
Yeah, plate tectonics wasn't really on their radar back then. The continuous fascination with the Antikythera mechanism, from cutting-edge academic research and painstaking conservation to its vibrant presence in popular culture, truly underscores its unique and singular position in the history of science and technology. It remains a powerful symbol of human intellectual ambition and engineering brilliance that transcends millennia. Outro.
This deep dive into the Antikythera mechanism truly shows us that the line between ancient and modern innovation isn't as clear-cut as we often imagine. This device, pulled from the seabed, is not just a testament to the astounding capabilities and sophisticated thinking of ancient Greek minds.
It really shifts your perspective.
But it's a silent challenge to our assumptions about progress itself.
If we connect this to the bigger picture, the Antikythera mechanism wasn't perfect in its mechanical execution. It might have even jammed after a few months, as some simulations suggest, due to the inherent limitations of hand-built parts.
Right, the mechanical limits we talked about.
But its theoretical sophistication and the engineering concepts it embodied, like the pin-and-slot epicyclic mechanism for modeling elliptical motion, were quite literally 1,000 years ahead of their time. It stands as a sole witness to a lost history of brilliant ancient engineering and remains a conception of pure genius, prompting us to reconsider what was truly possible.
It makes you wonder, what other incredible inventions from the ancient world might be waiting to be discovered, hidden beneath the waves or in the sands of time? Or perhaps we're simply lost forever, leaving the Antikythera mechanism as a lonely, tantalizing hint of a grander hidden past.
It truly raises an important question for all of us. How much of our own modern innovation is a rediscovery or a reinterpretation of older, brilliant ideas, rather than a brand new idea entirely? What ancient wisdom might we still be overlooking, something for you to mull over until our next deep dive?